In this video, we're going to look at the Fibonacci sequence of numbers. And to start with, let me tell you a little bit about the man that it's named for. The Fibonacci sequence is named for Leonardo of Pisa. His first name was Fibonacci, or I'm sorry, his family name, his second name is Fibonacci, and it's pronounced Fibonacci. You could see that the Italian maybe in it. But Leonardo Fibonacci was from Pisa, the same place as the Leaning Tower of Pisa, I would believe. And he lived quite a long time ago. But of the many mathematical things he is attributed with or known for today by mathematicians, the one that he is the most well known for among non-mathematicians is probably the Fibonacci sequence, because even those in the science field and even communications, English, psychology, other fields that know anything about Fibonacci, it's probably this particular sequence of numbers. Well, I'm going to get to the sequence in just a minute, but here's how he described his sequence. He said a certain man put a pair of rabbits, notice that it's a pair, in a place surrounded on all sides by a wall. So in other words, he takes a male rabbit and a female rabbit, puts them in a pen somewhere where they can't get out. No one can jump in, no one can jump out. How many pairs of rabbits can be produced from that pair in a year? If it's assumed that every month each pair begets a new pair, which from the second month becomes productive. In other words, during the first month of these bunnies' lives, they're considered a baby bunny, and they don't reproduce yet. But then in their second month of life, they're already past puberty and reproducing. So when we look at that and say, okay, so how many pairs are there at any given time? Let me just clarify. If this is our first set of bunnies, our first pair, then in the next month they're big, so they're adult, mature bunnies. And now they're going to stay mature all the way through, right? So we're going to select this purple ones is the first pair. And then the first time we get another new pair is in month 3. So in the second month, our first pair becomes mature. And then in the third month, here's their first children, let's say. Now the following month, that first set of children is now mature. So these green ones are the second pair, and you can see them month after month as they continue to be adults. And every month they get busy and produce a new pair. And then by the month 1, 2, 3, 4, by month 4, here's our one pair of babies. Now that one pair of babies came from the original pair, right? So here's the original, the adults, the granddaddies, or I guess the grandma and the grandpa. And the following month, this blue one is who they produce. And then the month after that, that blue one's no longer a baby. Now, by the time we get to month 5, notice that both the purple pair, let me get another color. How about orange? So in this month 1, 2, 3, 4, 5, yeah, in month 5, notice that the purple pair creates their children, and the green one, the green pair, here the green pair is being counted for themselves, and then here's the green pair of bunnies, first set of children. But so on. If you kept going like this, after month 5, the next month, there's going to be, I don't know if you've already calculated this, but the next month there's going to be a total of 8. And after that, it'll be a total of 13. And after that, a pair of 21. I'm sorry, not a pair, but 21 pairs. So in the first month, there's 1 pair. In the second month, there's still only 1 pair because these babies didn't start reproducing yet because they're still babies. In the third month, we've got 2 pairs because mom and dad now have their first set of offspring. In the fourth month, we've now got 3 pairs. We've got mom and dad, their first set of offspring, and now their next month's offspring, the babies. And in the 5th month, we've now got 5. We've got the original pair, the first set of babies, the second set of babies, and now we've got a third set of babies, plus the first set of grand babies, and so on down the road. If you looked at this as a sequence, oh, whoops, got out of sequence here a little bit. I meant to add something before we talked about Pascal. If we looked at these numbers, we'd have 1, 1, 2, 3, 5, 8, 13. And I don't know if you've already seen the pattern. How do I get the next set? You don't want to keep counting bunnies. Let me tell you that the way we'd get the next pair here, the next set here, or the next number, is you add the 2 before it. So if we add the 8 to the 13, we'd get a 21. Going back to this 2, where did that 2 come from? Add the 2 numbers before it. So add the 1 and the 1, and that gives us a 2. Add the 1 and the 2, and that gives us 3. Add the 2 and the 3, that gives us 5. And so on. 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on. Could you keep going? And notice that this is not finite. Finite would mean that it ends. But notice with this ellipsis, the sequence just keeps going and going and going. There's not a last one. We cannot count all the Fibonacci numbers. So it's not finite. Instead, we'd call it infinite. The Fibonacci sequence is an infinite sequence. It doesn't end. It does have a pattern, but it keeps going and going and going. The set of Fibonacci numbers is an infinite set of numbers because it doesn't have a last number. It keeps going and going and going, and it doesn't end. So that's one more thing you could say about Fibonacci. What you should be able to do in your notes is have a list about Fibonacci and a list about the Fibonacci numbers or sequence. Numbers are just the elements themselves, the 1, the 3, the 2, the 13, the 21. Those are all Fibonacci numbers. The sequence is when I put them all in order. If I'd said 1, 1, 2, 3, 5, 8, 13, and so on, that'd be the Fibonacci sequence. But you should have a list of things you know about the Fibonacci numbers or sequence, the things you know about Fibonacci, the mathematician, and as you continue through this video, you should be able to keep going and going through adding more and more to that list. You might even do, after you've read the section, you might even do an internet search. Just type into your internet browser Fibonacci sequence or Fibonacci numbers, and you'll find even more cases of how the Fibonacci numbers show up in nature. In the pineapple, in the pine cone, in a sunflower, in a nautilus shell, a number of things. But we're going to look at 2 different places that the Fibonacci numbers shows up, not in nature, but two things about the Fibonacci numbers that just comes up in a pattern else in other patterns. So the first one is going to be looking at what we call Pascal's triangle. So here we have another mathematician named Pascal. Let me be really clear that I'm talking now about a whole different pattern of numbers. I'm going to circle back to how this Pascal triangle has something to do with the Fibonacci sequence. But don't be confused now that how you get the Pascal's triangle has nothing to do with how you get Fibonacci numbers, other than the one thing that they do have in common is you use addition for both the Fibonacci numbers and Pascal's triangle. But that's the only thing that they have in common with regards to how you create them. But again, we'll circle back to what they have to do with each other. But this is Pascal's triangle. It starts with a 1 at top, and then you have ones on each side. And those ones on each side continue, but the number in between is going to be what you get when you add a 1 to a 1. The two numbers above it add to the next number. So again, we're going to start with a 1 on the outsides, but on the inside for the Pascal's triangle, if we add the 1 and 2, we'd get 3, add the 2 and 1, and get 3, and so on. Notice that I really only have to think about the addition for 1 plus 2. So 1 plus 2, or if you're using a calculator, 1 plus 2, you don't have to put that in once to get the 3. When we get to the other side, because it's symmetric, the 2 plus 1 is going to be the same as 3 because addition is commutative. So think that through as you're going. I know adding the 1 plus 2 is easy enough, but when you get further down and you're adding like 28 and 8 to get this number over here, you don't have to do it again when you get to the other side and you're doing the 28 and 8. So notice that pattern. But this is what Pascal's triangle would look like if we finish it out. You should be able to create Pascal's triangle for 7 or 8 rows. Mostly, though, make sure you understand how to get the next row. So if you were given any of these rows of Pascal's triangle, could you create the next row? Or if you were given 2 Fibonacci numbers in the sequence, could you tell what the next number in the sequence would be? You should be able to do both of those things. Here's something else we can notice about Pascal's triangle. If we called the top row 0, and then row 1, 2, 3, 4, 5, 6, 7, 8, and so on, if we added up all the numbers in row 0, we get a 1. Add up all the numbers in row 1, 1 plus 1 is 2. Add up all the numbers in row 2, 1 plus 2 plus 1 is 4. Add up all the numbers in row 3, 1 plus 3 plus 3 plus 1. Here's the sum, 1, 2, 4, 8, 16, 32, 64. Some things that you should notice about a pattern here. First of all, the easy part of the pattern is that it's just doubling every time, right? So if you hadn't been given the 128 and the 256, and you didn't want to actually add them all up, we could do the 1 plus 7 plus 21 plus 35 and so on. But we could also take the 64, and you might notice that it doubles. Adding these numbers up or taking the sum of the row above it and doubling it gives us this number. So the 1 plus 8 and so on, all along row 8, is going to add up to 256, which is just 128 doubled, which to me, that's a lot easier problem than adding all of these up. So that's one pattern about the sum. So this idea that you double the sum above it. But can you see another pattern about the sum? So in other words, if we were missing several rows, so let's say that we didn't have, let me block these out. If we didn't have any of this, could you have come up with this 128? If we didn't have those rows above it, would you have been able to get this that this sum was 128? Or in other words, can you use the 0 for row 0 and get 1? Use the 1 to get 2. Use the 2 to get 4. Use a 3 to get 8. How can we use a 6 and get 64? It's going to have something to do with doubles or with times 2. And here's what the pattern is. You could pause the video now if you don't want the spoiler, if you want to think through it and try a few things. But try multiplying a 2 by itself that many times. So 2 times 2, 2 times. 2 times 2 times 2 times itself 3 times. 2 times itself 4 times. Two times itself 5 times, and so on. 5, 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Gotta squeeze another 2 in, 8, or so on. Or in other words, if we said 2 to the nth power, and that's the pattern that we were going for. How does that work with a 0? Well, 2 to the 0 power is 1, because anything to the 0 power, if you recall, anything to the 0 power equals 1. So there's a pattern we can use to get the sum of the rows of Pascal's triangle. So the answer here is that the sum sub n, the sum of the nth row is 2 to the nth power, and that's it. Well, what does this have to do with Pascal? Oh, wait, one more time. I left this blank so we could write this in, that it's 2 to the n. Two to the n is the sum of the elements in row n. What does this have to do with Fibonacci? Well, I don't know if you saw, oh, let me flip back here. I don't know if you can see, when you look at these numbers, if you can see all the different patterns. Here's a pattern. Notice here we've got the 1, 2, 3, 4, 5, 6, 7, 8. There's an easy pattern. There's a number of other patterns built all the way through here. Let me just throw one out at you. If you were doing this problem, you have a class of, let's say, 10 students, and you want to choose them into groups of 2. How many different ways can you place all 10 students into groups of 2? How many different ways could those 10 students be paired up? Not how many groups can we make, because that's easily just 5, but how many different ways can we take 10 students and make groups of 2? How many different sets of groups can we make? That answer is found here in Pascal's triangle. That's just one of many things. There's a number of things in Pascal's triangle that answer a number of math questions, and I'm not giving you the answer to that last one, but that is one you could find pretty easily if that sounds curious to you. But here's where Pascal meets Fibonacci. Let me clean it up just a little bit. Those shading here. If you look at what I've colored in, let me draw a line between each set too to make it, I don't know if that makes it more confusing or less, but let me go back and undo that. When we see what I've got highlighted, if we add up what's in the diagonal that I've got, the first diagonal has a 1, that pink diagonal has a 1, the blue diagonal, 1 plus 1 is 2, that yellow diagonal, 1 plus 2 is 3, the purple, or the green rather, right? Green comes next. The green diagonal is going to be 1 plus 3 plus 1 is 5. And then the purple diagonal, 1 plus 4 plus 3 adds up to 8. Then we've got that orange diagonal. Did you guess it, that it's 13? And without adding them, do you see that this pink one is going to be 21? Because we get the Fibonacci sequence again. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8, 13. 8 plus 13, 21, and so on. So that's how I promised that by the end of the video we'd circle back and say what Pascal had to do with Fibonacci, and that's an excellent question. What does Pascal have to do with Fibonacci? And I want to encourage you to be able to answer that question. Let's look at one last connection we can make with Fibonacci sequence in other numbers, and this is a golden ratio. Now, what is a golden ratio? The golden ratio is approximately 1.618. What does that mean? That if we have a golden rectangle, that if the width was 1 foot, then the height is 1.618. Now, our paper is 8.5 by 11. If I divided that, 11 divided by 8.5, I get 1.294. I should have looked this up before I started the video, but if we had someone here who is familiar with the A4 paper in England, I think they call it 4, but in England, their standard paper is a little bit closer to this ratio of 1.618 than our paper is. But when we divide these numbers, we're going to get kind of close to this golden ratio. Go to the Greek Parthenon in Athens? And that Parthenon, the length across the front compared to the height falls precisely into this pattern, this ratio. The body, the human body, has this ratio all over it. You could look some more of that up also. I don't want to go into too much detail of that because I'm not as interested right now in the ways that the golden ratio shows up. I'm more interested right now in what the golden ratio has to do with the Fibonacci numbers. So let's get back to the Fibonacci numbers. And the golden ratio precisely is the square root of 5 plus 1. So 1 and this 1 square root of 5 divided by 2. And that number will give you approximately 1.618. It's a irrational number that keeps going and going and going, but if we rounded it to 3 decimal places, we get 1.618. Let's see what that has to do with the Fibonacci sequence. Here's the numbers, 1, 2, 3, 5, 8, 13, 21. And notice if I take the second number and divide it by the first, I'd get a 1. Take the third number, divide it by the second, 2 divided by 1. Take the third number, divided by the third, and I'd get 1.5. If we took the 5 and divide it by 3, I'm going to get 1.66 repeating, so let's just round it to 3 decimal places, 1.667. 8 divided by 5 is going to give us 1.6. 13 divided by 8 is going to give us approximately 1.625. 21, or actually that one's precise. 13 divided by 8 is exactly 1.615, or 625. 21 divided by 13 is approximately 1.615, and so on. If you take any two Fibonacci numbers and divide them, the farther down the row in those numbers that you get, the closer this number will approach the 1.618. The farther along you go, in the Fibonacci sequence, the closer that ratio gets to the golden ratio. So interesting. If you have any knowledge of architecture or art, why is it that the human people are drawn to a rectangle that's shaped with this ratio compared to a rectangle that's shaped otherwise? Why is it that that seems more natural that we're drawn to? Is a psychological question, but mathematically it's been found again and again to show up in what's more pleasing in art, but also it shows up in this Fibonacci sequence and elsewhere. Well, that's just a little bit about Fibonacci. I hope that you'll read and watch the book video to get even more. And then when you jump in to do the homework, if you have any questions, please email me or bring them to the office if we have some virtual office hours. But don't leave your questions just to wait, because your luck would be that the one question you have that you didn't ask will end up being on the test, right? So if there's anything about the Fibonacci sequence or anything about the homework in section 5.8 that you would like to ask about, please don't hesitate to ask. And thank you for making time to watch this video.